Let's look at how to sketch a function f of x when you are given information about either the derivative and or the second derivative. And if you want to print this sheet, I'm going to be working a few problems right here off of a sheet that I handed my students. And if you want to print that so you can have something to write on, you can go to this bit.ly link right here. That should open it up for you. Big picture reminders. These are things that if you are to the point where you are sketching curves, you should already know these things. Your derivative tells you the slope of your function. Therefore, if your derivative is positive, your function increases. Derivative negative, function decreases. All of these things, I'm not going to read them to you, but these are things that you need to know in order to curve sketch based on the information that is given to you. So if you want to copy that down, you can pause the video, and I am moving on right now. Okay, so let's look at number one, and let's piece this information together and see if we can figure out what f of x would look like. And so the top line tells me that f prime of 0 and 4, I'm giving you very specific x coordinates, and at those x coordinates, the derivative is 0. That means my slope is going to be 0 at those x coordinates. So when I get to x equals 0 and x equals 4, my function should be horizontal. And typically those horizontal spots are temporary. They're only at points. You don't typically have prolonged times where your function is horizontal. If your derivative is positive, that means your function is increasing. So I'm going to make a little note to myself. F is increasing. Derivative negative. F is decreasing. Second derivative, now we're getting into concavity. Second derivative positive, that means your function is concave up. Second derivative negative means your function is concave down. And just a note for you, these are little notes I'm making for myself. I'm not turning any of this in to be graded, those little notes to myself. I don't condone the use of things like arrow up for increasing or CU for concave up. But again, I'm just making notes to myself. So that's why I'm being a little bit lazy in my notation right there. So let's put this together. And the way I organize it is I start by looking at my first derivative, and I'm going to ignore the top line for a moment. I'm going to look at the things that happen over intervals. So like for all negative x's, my function should be increasing. So what I like to do is across the top, I'm just going to make a note to myself, all of these x's over here, my function is going to increase. Then between 0 and 4, and again after 4, my function will decrease. Now I could have actually said we decrease from 0 to infinity. For some reason I chose to split it up at 4, but that's fine. So we're going to decrease, and then we will decrease some more after that spot. And at those transitions, when I change from increasing to decreasing, I have a slope of 0, which is typically the case. And then here I decrease, I will have a slope of 0 at 4, and then I will decrease some more. And then as far as concavity, between 2 and 4, so here I'm between x equals 2 and x equals 4, I'm going to make a note to myself that I am concave up. And then everywhere left of 2 and everywhere after 4, we are concave down. So this is how I kind of organize my work here, organize my thoughts. Then I look at this and I try to figure out how I'm going to piece all of this together. And one thing that I don't like about this particular problem is I didn't give you any explicit points to hit. And just peeking ahead, I'm going to do number 4 next. Number 4, I tell you that f of 0 is 1. That means I need to hit the point 0, 1. F of 2 is 5. That means we need to hit the point 2, 5. So the first thing I'll do on number 4 is actually plot those points 0, 1 and 2, 5. Right? So that's kind of nice. Having points to aim for makes things easier. Number 1, I didn't give you any points to aim for. And so this one's actually a little bit more of a difficult one to start with. But whatever, we're already this far in. So I'm looking here, and across the top, I can tell that my function is going to increase. I'll have a slope of 0. We will decrease. We'll have a slope of 0 again, and then we'll decrease. If you want to make this really bad, that's increase, slope of 0, decrease, slope of 0, decrease. But in doing that, I completely ignored my concavity down here. So what I have to do is find a way to merge those two pieces of information together. So if you think about a concave down graph, if you were going to sketch a concave down piece of a graph, it would look like that. And for this first piece left of the y-axis, we want the part of concave down where these slopes are positive. That's going to be where you're going up, like so. And so, should I have done that with my other hand? I don't know. Anyway, so over here, I'm going to piece that together by left of the y-axis doing this. I will increase while concave down, keeping in mind that when I get to the y-axis, I should be horizontal. Now, I just happen to hit the y-axis at 4. I could shift that up or down as much as I want, and I'm still satisfying the increasing and concave down piece. I'm just going to leave it right here. And then After that y-axis, I need to decrease while still concave down. We're concave down until we get to x equals 2. So now I will decrease while concave down. At x equals 2, we will continue to decrease from 2 to 4, but we will transition to concave up. So now we're decreasing while concave up. So I need to decrease while concave up until I get to x equals 4, because at that point I should have a 0 slope, and then we will continue to decrease, but we will flip to concave down, and here is a good graph for number 1. And you can shift that up or down as much as you want because I did not give you any explicit points to aim for. So there's number 1. What is that? I just want to erase this. So there's number 1. And I think the next one I wanted to do was number 4. I am not doing every problem on that sheet that I linked earlier. Okay, so I've already started number 4 a minute ago. I've plotted the 2 points that we're going to aim for. And notice here, I only gave you first derivative information. There's only first derivative information. And so if your derivative is negative, that means your function is decreasing. If your derivative is positive, that means your function is increasing. And so I'm going to make a note over here. Left of 0, we're decreasing. And then after 2, we will decrease. And then between 0 and 2, my function will increase. And this is going to be really nice. Most people, when you see that I need to decrease, increase, decrease, most people will draw this in a nice, smooth way. I'm going to decrease, hit that point, increase, hit that point, and then start to decrease. Most people will make that pretty smooth because that's the way we tend to like to draw things. However, because I mentioned nothing about concavity, you actually could satisfy this information by zigzagging it. Linear pieces, line, line segment, line segment. You could do something like that. That kind of looks dumb to me though. So I am going to draw a nice differentiable function. So I'm going to be decreasing to that point, increase to this point. Whoa, yeah. Well, something like that. That's not very pretty, but that's all you have to do. That was kind of nice. Only first derivative information. And then the last one I want to look at is number 6. And this gets a little bit more complicated. Again, I don't think I chose very good problems. This one only has first derivative information also. The main reason I zoned in on this one is because I like this piece of information down here. And I'll talk about that in a minute. So f of 3 is 0. So that's an ordered pair. I'm going to go ahead and plot the point 3, 0. 3, 0. F prime is negative. That means that f is decreasing. F prime is positive. Means f is increasing. And then f prime of 3 is 0. That means when I get to x equals 3, my slope should be 0. And we had something similar to that on number 1. Number 1, the very first piece of information was that the slope was 0 at x equals 0 and x equals 4. And for number 1, all I can do is make this little note right here where the slope is 0 at those points. On number 6, however, I can do a little bit more because I know the slope is 0 when I get to x equals 3, but I also know the y coordinate. So when I get to this point, I need to be horizontal, and I'm going to put that little reminder to myself by putting a small horizontal segment through that point so that when I get to it, I'll remember I need to be horizontal as I go through that point. So let's piece the rest of this together. So f is decreasing left of 0, decreasing left of 0, and after 3, we are increasing between those two. And that alone, if I want to decrease, increase, decrease, I want to do this. I'm going to have to erase it, and you'll see why in a minute. I want to do this. Decrease. Oh, that was bad. Decrease, increase, decrease. I want to do that, but I threw an extra piece of information right here. It says f of 0 and f prime of 0 does not exist. That's a little bit of an interesting way of wording that. If I only said f of 0 does not exist, if your function does not exist at a point, then the derivative definitely won't exist. That would be a discontinuity. That would be a non-differentiable point. So when I said f of 0 and f prime of 0 equals 0, that does not exist. That's a little bit overkill. I shouldn't have included the f prime of 0. However, if it's only f prime does not exist, now we have some options. If that's all you know, your options are we could have a cusp, we could have a discontinuity, or we could have a vertical tangent. The vertical tangent's pretty rare, but it is one you need to be aware of. So those are the three options if only your derivative does not exist. However, since we know that the function does not exist as well, that eliminates the cusp and the vertical tangent option, and there must be a discontinuity. So to satisfy that, there are several ways we can do that. The easiest, since I already have this graph drawn, the easiest would be simply to erase the graph on the y-axis and put an open circle. And put a removable discontinuity. Now my function does not exist and my derivative does not exist. We have other options though. We could have a jump discontinuity. I could be decreasing here, jump down here. Now I'm increasing. I have a slope of 0. That satisfies the given information as well. The other type of discontinuity we could have, we've already covered removable and jump. By the way, make sure you don't accidentally fill in one of these spots, because if you do, you are defining f of 0, and we're not supposed to. The other option would be to have an infinite discontinuity. So I could decrease and turn the y-axis into a vertical asymptote, come up this way, have my slope of 0. And remember, we do want a slope of 0. I didn't write that up here. We need a slope of 0 at 3. And so that will be the third option as well. So you have 3 different options to satisfy the non-existent derivative and the fact that the function is not existing as well. And I think that's good enough.